Hey there, everybody. We're going to look at section 4.2, and if we have time, we'll move into looking at section 4.3. So let's see how much time we have for that. So the first idea is to find the approximation of an area is to create rectangles. Now, there's two ways the rectangles can hit. Either you're going to have the left side of your rectangle hit, and this first rectangle here would be 0, or the other option is to use the right side of your rectangle. If you notice, you're going to have very similar ways of solving it, but the only thing that's going to be different is the end point and the beginning point. And if you look at these two situations, they're going to be different. And so this would be my lower bound because it is, looking below the actual, and this would be my upper bound because this is more than what the area actually is. And where this section goes is then we say, well, you know what? Let's make them even smaller. And as we do a limit, as the number of rectangles goes to infinity, we will get the actual area. And so we're going to really build towards this idea. And so there's a lot of notation involved with these. Here we're going to show you how to tackle those. For these types of situations where, look at this, you have 1, 2, 3, 4, 5 rectangles. Could you just write it out and say, I've got this rectangle, it's this high, this rectangle, it's this high, this rectangle, it's this high? Yeah, go for it. But for these ones where we take the limit as n goes to infinity, we need to have some shortcuts. And I think you've seen it that you're going to have to do some summations with I squared, I cubed, and you're like, I have all this stuff going on. And so that's where we're going to go. First is knowing these four summation formulas. Definitely do that. So let's say I had a sum n times starting with I equals 1 of just some number like 5. Well, if I were to add those up, 5 plus 5 plus 5 plus 5, right? N times, that'd be the same thing as saying 5 times n. If my n here was 20, how many 5s do I have? I have 20 5s. And how would I do that quickly? I do 5 times 20. And so what these are shortcuts to help us find the summation quicker. These guys here they look really complicated, but if you just plug in numbers and you're saying, hey, I've got just I. And so every time n goes up, so does I. Well, this is a way of finding out what the summation would be. So where this section really goes is here, is the definition for the area of a region. And so what this picture does, it really looks at, I'm going to focus on one triangle. Sorry, one rectangle. I can't believe it's called a triangle. I'm sorry. And I'm trying to erase this. And so I'm going to look at this one rectangle. There's two components to knowing the area of that rectangle. The height, the function at this x value. And the second thing is the width. Well, what's that width? If I think of this rectangle, my width is delta x, and my height is the function. But the key is it's the function of that particular, that one rectangle. And so I need to look at that specific one. And so this c sub I is basically saying the ith rectangle, and the x value is going to be c. And so if you look, the area, the exact area, is going to be the limit as n goes to infinity. In other words, keep getting more and more rectangles. The height of your rectangle times the width of your rectangle. How do you know what your width is? The width of your rectangle is b minus a over n. So b is your ending point, a is your starting point. The difference of the two divided by n, that's going to be your width of them. Okay. All right. Just so you know, in the next section, we have a way of doing this very quickly. It's called the fundamental theorem of calculus. I have no idea what's happening to my pen, so I'll try to get that fixed for the next slide though. All right, so what we have here is, these are some problems. I think the best way to show how to do this is to do a problem. So 47 to 49 are nice, but the thing I don't like about them is they go from 0 to 1. So you can't visualize what's going on as well. 51 I like because we're dealing with squares, we have a lot to deal with, and it's going from 1 to 3. So we're going to see what happens when you don't start at 0. Some of the examples in the book usually go from 0 to 1, and they kind of generalize it. Definitely look at those examples, but this is going to help us even more. So we're going to start by looking at number 51. And so the key to this whole thing, we're going to start, the area for this is going to be the limit as n goes to infinity of the summation of n, starting with the first rectangle, of the function height times delta x. And so what we're going to do is we are going to start by looking at delta x. So the delta x for number 51 is, if I look, I'm going from 1 to 3, so my total distance horizontally I'm going to go is 2, and the number of times I'm going to do it is n. So my delta x is 2 divided by n. Okay, that's your first step in doing anything. The next is, what are your function values? Well, so I'm going to rewrite everything I got. So the limit, sorry about what my pen's doing, is n goes to infinity of the summation of the function. Now, here's the key. I'm starting with at 1, and I'm adding these rectangles. So as I add those rectangles, each new rectangle is moved to the right a little bit. And the amount that's moved to the right is the width of the rectangle and I have this I here, which is then going to tell me which rectangle it is. So it's the function value of 1 plus 2i over n times the width, which is 2 over n. Okay, so let's plug in. So what does this function look like? Well, my function is 16 minus x squared. And what's my x? 1. I'm going to rewrite this. So we're back. So I have the limit as n goes to infinity of the summation of my function, which is 16 minus x squared times 2 over n. And so the limit as n goes to infinity of the summation of 16 minus, well, what's my x value? My x value, and that's the key. So my function's x, but what is my x as I plug it in? My x is 1 plus 2i over n, and so I have the limit as n goes to infinity of the summation of, I'm going to have to FOIL this out, 1 plus 4i over n plus 4i squared over n squared, all outside is 2 over n. And so now I have the limit as n goes to infinity of summation of 15 minus 4i over n minus 4i squared over n squared. Now outside I have 2 over n. You're noticing there's a lot of algebra involved, but we're gonna come up on some ways we can simplify it. So what I have is the limit as n goes to infinity of the summation of 15. But notice that's times 2 over n, so that's got a 2 over n outside of it, minus the 2 over n times the summation of 4i over n minus 2 over n times the summation of 4i squared over n squared. And so if I were to rewrite this, you're going to see I can simplify this. Is that first one stays the same, right? The next one, I can factor out a 4 over n. So I really have 8 over n times the summation of I. The next one, I could take out a 4 over n squared. So I've got 8 over n cubed times the summation of I squared. So when I take the limit, my first one becomes 15n. My next guy, the summation of I. Summation of I is, so I still have my 8 over n, but my summation of I is n times n plus 1 all over 2. And then my summation of I squared is going to be n times n plus 1 times 2n plus 1 over 6. I have a complete mess, right? So first one's easy. You get 30, okay? Next one, not as easy. You get 8n plus n times n plus 1 all over 2n, okay? Last one, you get 8 times n plus 1 times 2n plus 1 all over 6n cubed. Now, right at this point, if you had not done an infinite limit, you could just plug in n, right? But since we're taking n to infinity, we're going to need to think about what's going to happen here. These, if you look at these ones right here, these are rational functions. And if you look, the top has n, sorry, let's go back. The top has guys, I just noticed a mistake. This should have been an n squared. This should have been an n squared. So I have an n squared here. Okay, so so the top. So if I look at that second term there, I have n squared on top. I have n squared on bottom. And if you remember what you know about rational functions, if I were to do long division, I could divide that n squared into everything, and I would be left with my leading coefficient, which would be 4. So when I take, so this is saying I'm going to take the limits as n goes to infinity, and then here, when I actually take it, the limit as n goes to infinity of 30 is 30, but the limit as n goes to infinity of this is going to be 4. And the limit of this one is, well, I've got n, and n, so that's n cubed. And on the bottom I have n cubed. But if you look, I've got 8 times 2. So my leading coefficient on the top is going to be 16. And on the bottom it's going to be 6. So I'm going to have n cubed divided by n cubed. So it's going to limit out at 16 sixths. And so I've got 26 minus 8 thirds. All right, that was probably the hardest screencast to watch ever, and I will try to fix things up for you next time. But sorry about the pen, but I wanted to get that to you. All right, have a good one.